So thank you for the introduction there. My name's Amin. I'm based at the University of Nottingham in the UK, and I'm part of the experimental spintronics group here. And today it's my pleasure to present some of our recent work alongside our collaborators. And we've been looking specifically at these antiferromagnetic half-skyrmions, which we electrically generate and control using electrical pulses in room temperature devices. And the QR code there, which I'll show at the end as well, just links to the archive paper that we submitted last month. So without further ado, just to introduce what I mean by a half-skyrmion and why we care about them in the field of antiferromagnetic spintronics. They resemble a whirling texture in the magnetic order.
Sorry, Oliver. It seems there is a problem with your screen, with the screen you're sharing, because we can see a few dark spots. I don't know if you can minimize. Okay. I guess they are from Zoom. I don't know if you can minimize those small screens.
I'm not too sure how to collapse this bar, I'm afraid. Let's see. There we go. Has that improved?
We can see, at least I can see still two. Yeah, another one at the bottom.
Okay, that's strange. If I stop sharing and reshare, maybe I can.
Maybe it can work. Yes, let's try to do that.
Apologies about this. Let's try this. Has that improved at all?
I still can see a few. I don't know if somebody in the chat can confirm this, but for me, I see now it looks better. But for example, I cannot see your title in your slide.
You see the title there?
Yeah, I can confirm there on the right, for example, there's a big rectangle hanging around. Looks like you're having the participants of Zoom there. Maybe you can minimize that.
Yeah. Okay.
Okay. Now it looks.
There's still something left on the top, but if you don't come close to that.
Yeah, sure. I won't go near that top bar, so it won't expand. Okay.
Okay. Thank you. Sorry
about that. So these textures, they resemble a whirling structure in the magnetic order. And in terms of their behavior, they're small and their dynamics resemble, and their rigidity resemble particle-like behavior. And that's largely because of their topological protection. So if I present an example of an antiferromagnetic meron or half-skyrmion here, we can see that for a collinear antiferromagnet, we can consider these two separate compensated magnetic sublattices, which I've separated here vertically. So if we consider just the top sublattice, the spins in this case can resemble the half-skyrmion in a ferromagnet, where the spins at the core of the structure point out of plane, and as we move in the radial direction to what's called the container far away from the core, you can see that the spins then align in the plane of the material. And the topological charge for that type of structure is a half, which is where the name half-skyrmion comes from. And then likewise with the bottom sublattice, which is the time reversal partner of the top sublattice, the topological charge is the opposite sign. So the naive expectation here is that when taking this whole structure, you might expect that the topological charges will cancel, giving no topological charge overall. However, for the case of an antiferromagnet, we typically consider what's called the nail vector. So that's the antiferromagnetic order vector. And in that case, doing the same calculation for the topological charge will give you a finite number. And so why are we interested in these structures? Well, due to their topology, they can be stabilized to very small sizes, down to tens of nanometers. They're expected to be propelled at very high velocities using simple electrical current pulses. And as such, they're expected to be useful as bits of information in skyrmionic devices. So you can imagine them in some kind of bit register as carrying the bits of information. With this small schematic, I show the driving mechanism, which is important in an antiferromagnet, because if we consider the two magnetic sublattices again, in a ferromagnetic case, when driven with an electrical current, these topological structures can have an unwanted transverse deflection called the skyrmion Hall effect. And I've indicated with the red and blue arrows the gyrotropic forces that give rise to that skyrmion Hall effect. But in the case of our two compensated magnetic sublattices, you can see that those gyrotropic forces, remembering that Q here, the topological charge, is of opposite sign on the two sublattices, they actually cancel each other out so that we're just left with this driving force that is collinear to the current direction. So in this sense, we're able to use antiferromagnetic topological structures and drive them in straight lines along tracks that we fabricate from our material. So just to go over some of the experimental details, the material system that we're working in with here is a collinear antiferromagnet called copper manganese arsenide, which has been quite the workhorse in the field of antiferromagnetic spintronics over the last few years. And this material is a collinear antiferromagnet with a nail temperature well above room temperature at 480 Kelvin. And the electrical properties are that of a semi-metallic material, which makes it an ideal material for making electronic-based devices. And alongside that, the crystal symmetry has the required hidden symmetries that give rise to a nail spin, current-induced nail spin orbit torques, which have been shown previously to efficiently manipulate the antiferromagnetic order. So from this material, we have a layer which we pattern a cross-shaped device, and the arms of the cross here are 10 microns wide. We pattern this cross using chemical wet etching, and then the arms of the device we electrically contact to by bonding. So we're able to apply current pulses along these arms. And we travel with this device to a synchrotron facility called Diamond in Oxfordshire in the UK. And at one of the beam lines there, we're able to image the magnetic domain structure using a technique called XMLD PEEM. So that's photo electron emission microscopy. And in the bottom image, I give a simple example of how that technique works. We have incident linearly polarized X-rays, which are incident with a grazing angle of around 16 degrees to our sample surface, and domains, magnetic domains in the material where the nail vector is perpendicular and parallel to the polarization of the X-rays appear as light and dark contrast respectively. So if I zoom in on one structure that we imaged in one of the arms of this device, here I'm identifying a 180-degree antiferromagnetic domain wall. So you can see that the contrast goes from gray either side of the domain wall through white and black. So if you follow the nail vector axis through that structure, you can see that the nail vector axis is rotating by 180 degrees. Here we've got light contrast, which is perpendicular to the X-ray polarization, which I've shown with this double-headed arrow in the top right corner. And then black is parallel to the X-ray polarization. So here we're able to identify the nail order axis. Then we applied an electrical pulse along this arm, a 1 millisecond wide electrical pulse of amplitude 21 volts. And what we saw imaging after applying this pulse was that the domain wall fractured into multiple sections of reversed chirality. And I say that it's reversed chirality. I've highlighted another region here with the spins showing the nail vector alignment. And you can see that the contrast has swapped from being previously white to black to in this section being black to white. So that's what corresponds to a chirality reversal of the domain wall. And it's actually the pinch points at which, though, the chirality reverses that we're interested in. So using micromagnetic simulations, just one example of this chirality reversal, the 2 pinch points either side, we identify as being these vortex structures. So you can see from the top sublattice spins that they swirl in a typical vortex-like structure around that pinch point. And the outer plane component we identify, so that's shown by LZ here, the magnitude of LZ. We identify an outer plane component, which gives us our topology for these structures. So as such, we're able to identify that, in this case, the top vortex is a block type half-skyrmion. Block type because the spins at the container are perpendicular to the radial direction. And then the bottom vortex, you can see that there are 2 axes where the spins are along the radial direction, and then the other 2 axes where the spins are perpendicular to it. And that's typical of an anti-half-skyrmion or an anti-vortex. So these things come, when we get this chirality reversal in the 180-degree domain wall, what we've formed is a vortex anti-vortex pair, and we know that they are topologically non-trivial based on these micromagnetic simulations. So our next aim was to see what would happen when we applied subsequent pulses with alternating polarity. So this is after a sequence of pulses with alternating polarity. So after each pulse, this is again in the starting position, I've identified the top 3 vortices for you to keep track of. After the first pulse with reverse polarity, you can see that those top 3 vortices shift up in the direction of the applied pulse. So they shift up along the domain wall length. And subsequently with pulses with the alternating polarity, you can see that you get a subsequent shift back down, back up, down, up, down, up. And in particular, looking at those last 4 images in the sequence, you can see that with alternating polarity pulses, the domain wall and the half-skyrmions are reaching these 2 stable states where they almost look identical. And so I was able to measure the displacement with which these vortices move to after each pulse. And we can see clearly here that for those top 3 vortices, there's this repeatable, reversible movement in the direction of the current pulse, which is commensurate with the theory. So we were quite convinced by these results that not only have we generated these antiferromagnetic half-skyrmions using a single 1 millisecond wide electrical pulse with moderate current density, and this is all done at room temperature, but then subsequent pulses were able to controllably move those generated half-skyrmions up and down the length of the 180-degree domain wall on which they're localized. And we see this as a crucial step towards realizing practical skyrmionic memory devices, as up until this point, there's only been one conclusive example of these type of structures being present in any other antiferromagnetic material at all, let alone being controlled with electrical pulses. So with that, I'd like to say thank you, and I'm happy to take any questions. And I'll leave the QR code for the archive manuscript there, just in case anyone's interested in reading further into it. Thank you.
Thank you, Oliver, with this for this interesting talk. I can see a question in the chat. So Jan asked if you can quickly comment on the effect of pinning. Is it stronger in FAM systems than in FM systems? So
pinning, that's a very good question. Pinning here definitely plays an important role. If I go back to the images of the sequence of pulses here, you can see that, as I alluded to, the last 4 images in particular show this. The positions to where the half-skyrmions move is quite clearly well defined. So there are clear pinning sites at the points to which they settle. And we suspect that those pinning sites are playing an important role in in stabilizing these structures as well, because our material has no DMI interaction, which is typically needed to stabilize these structures. So pinning in this case, we know is extremely important. In terms of comparing it to ferromagnetic systems, I'm not sure in terms of the relative strength there, but we know that it's crucial in our system for forming these stable positions to which the vortices move. I hope that answered that question.
I don't know if Jan is happy with this. I hope so. Otherwise, maybe you can chat in GatherTown later.
Sure, yeah.
Good. So thank you, Oli, for the nice presentation. I think
Thank you.